Welcome to this explainer. Today we're diving into something truly incredible. We're exploring an inspiring, heavily tech-forward solution to a massive resource crisis, and it involves using cutting-edge AI to solve a multi-billion-dollar problem that's literally flowing right beneath our feet.
Get this, according to the World Bank, the global economy hemorrhages a staggering $14 billion every single year. Why? Simply because 20 to 30% of all clean, treated water is just lost to undetected underground leaks. Now, in water-scarce regions that rely on highly energy-intensive desalination, this isn't just an inconvenience, it's a critical crisis. So, the big question is, how exactly do you find a leak you can't even see? Traditional methods are simply way too slow and honestly highly inaccurate.
Well, to figure that out, let's look at building the smart testbed.
A brilliant team of engineering students over at the University of Bahrain decided to take this multi-billion-dollar crisis head-on. And they did it right from their own campus laboratory by building a physical, purely data-driven pipeline. They didn't just run software simulations, they actually constructed a 16.5-meter closed-loop PVC pipeline fitted with 4 controllable leak points. This created a highly controlled environment to perfectly simulate underground failures and train their intelligent system. It's a remarkably sleek hardware setup. It routes the water through highly precise flow meters and pressure transmitters, while incredibly sensitive underwater hydrophones capture the acoustic data. And all of that raw information feeds straight into an Arduino Mega microcontroller. That microcontroller is the exact junction where the physical pipeline connects to the digital world. Its robust processor simultaneously samples both the hydraulic and acoustic signals in real time without skipping a single beat. All right, so we have the setup. Now comes the hard part, listening for the leaks. Think about it. The AI literally needs to hear the faint whisper of a leak over the roaring rush of water inside the pipe. It's kind of like trying to hear a pin drop in a packed stadium. But when you compare the baseline acoustic signal to the massive spike that happens during a breach, you can see exactly what a leak sounds like to the computer. And we see that exact same undeniable digital footprint in the pressure data too. A steady, normal stream will abruptly plummet the very moment a valve begins leaking. Having all this data is great, but making sense of it, that requires the AI brain, ANFIS. To process all these complex sensory signals instantly, the team chose ANFIS, which stands for Adaptive Neuro-Fuzzy Inference System. I know, it's a mouthful, but it essentially acts as the ultimate digital brain for understanding nonlinear fluid dynamics.
What makes ANFIS so incredibly powerful is that it brings together the best of both worlds. It combines the eyes and ears of neural networks, which learn and adapt to raw data patterns, with the brain of fuzzy logic, which applies strict if-then rules to make highly accurate decisions.
So the raw sensor data actually maps through multiple layers of nodes in the architecture. The neural network side tunes the parameters, while the fuzzy logic side outputs a crystal-clear prediction of the pipeline's exact status. To really maximize precision, the students hit this with a 1-2 AI punch by cascading 2 separate models. Stage 1 figures out exactly where the leak is, and that specific location data feeds directly into Stage 2, which then calculates exactly how bad the leak is. When you look at the live interactive workflow, you can see that location data dynamically feeding right into the severity model. The system instantly converts raw voltage into actionable infrastructure data, quantifying the water loss in real time.
Okay, so the system is built, trained, and ready. It was time for the successful live demonstration.
After rigorous training, the live results were honestly absolutely staggering. The AI localized leaks along the pipeline with a maximum error of just 1.1%. It literally pinpointed these invisible leaks down to mere centimeters. And wait, it gets better. The predicted leak quantities practically mirrored the real-world data with near 100% accuracy. This dual AI system proved incredibly resilient, scaling perfectly regardless of any background pump vibrations.
So, where do we go from here? Let's talk about the future of smart water.
These students essentially proved that this is practically deployable today. By upgrading this exact framework with wireless IoT communication and edge processing, municipal water grids could continuously and automatically monitor hundreds of miles of pipeline. It leaves us with a pretty inspiring thought. The technology to end catastrophic water waste was successfully built right inside a university lab. If these students can use AI to hear a leak through PVC over a roaring pump, the real question is, How fast can we scale this globally to save our most precious resource? Thanks so much for joining me on this explainer, and keep exploring how AI is reshaping our world.